Hello class, welcome back to Electromagnetics. We're going to continue in part 6 of the course. Continuing our looks now that we have the tool bag of Maxwell's equations, we're wanting to look back now, take a step back and look at static fields and kind of work our way back up to time varying fields. So with that, today we'll look at Poisson and Laplace's equations. I want to first do a historical background, another one that you could likely guessed by today's topics for the lecture: education, the École Polytechnique. I guess this is in Paris. Here he studied under Lagrange. He later went on to work at this institution, but he was a co-worker of Laplace. This is his image. Again, maybe you can guess from today's topics. This is Simeon Denis Poisson. Lived in 1781 to 1840. So what are some notable things? Well, he published over 300 works, scientific works in his field. He was famous actually for being the loser in a great showdown that involved Fresnel. This was a competition that was held involving diffraction. So at that time, they were still trying to figure things out. And so at that time, there were two major theories about light. Number one was that light behaved as a wave, or that it was a wave. The second part was that it was particles, a flow of particles. Well, Fresnel did his part, or his argument, based on the first assumption that it was a wave, and Poisson challenged this theory as he backed the second part of this, that it was particles. Poisson argued that if you had a light source and you put an obstacle in front of it, and then you had a plane behind it, behind the obstacle, that there should be no spot in the middle of the shadow. Fresnel's analysis suggested that there should be a spot based on wave technology, that it would cause this ripple effect. And hopefully you have enough background now to maybe understand the 2 points of view and their two arguments. Well, what was the result of this showdown? Well, the competition judge declared a duel and therefore required an experiment to see who was right. So the experiment setup looked something like this. So we had here our light source. There's probably looked more like a candle or a lamp or lantern or something. Here is your obstacle. So it was a circular obstacle that should cast a shadow, and then some distance away you'd have this screen with the shadow of the circular object, and the point of contention was this spot in the middle, which they call Poisson's spot. Is it going to be there or is it not? I'll give you a minute. What do you think? Well, the result was there was a spot. So this meant that Poisson was wrong, at least in this aspect of his understanding of what was going on. So this meant, of course, that Fresnel was right. And it looks something like this. So the shadow behind the obstacle, looked at this, you can see the wave characteristics. And then, of course, here is the spot in the middle that was the point of contention in this competition. So even though Fresnel was right, we will see this is not the end of the story, because quite frankly, we still don't have a super good understanding of light and what it is. There's some instances where it does act and behave like a wave. There's some instances where it does act like a flow of particles, as Einstein showed us. And the stark reality is we cannot reconcile those two. The mathematics involved with both conflict each other. And so it's really quite interesting topic to study. So back to our lectures. Again, we're in part 6. This is the second mini lecture in that. And so again, we're going to introduce and discuss Poisson and Laplace's equations. So we want to continue our discussion from the previous lecture and recall from there that we can now define our electric field vector as the gradient of the voltage, negative of the gradient of the voltage in a space or in an area. So we can now do some substitution into Maxwell's divergence equation for the displacement current, and we can do that by constitutive relationships, right? So we know that D, the displacement vector, is simply, or is equated to the electric field and its and the permittivity of the medium that we're in. So that's what relates these two. So we can do a direct substitution. Well, because the permittivity is a constant or scalar, we can pull that outside, and so we're left with permittivity times the divergence of the electric field, or del dot E. And so we know then that this electric field from this equation up here, we can substitute in the divergence of the voltage. So we can substitute that in here into this equation. And we know from Gauss's law that this all, whichever one of these you want to pick, has got to equal to the total charge enclosed in the volume that we're talking about. That's back from previous lectures on Maxwell's equations. So finally, what we're left with then, is we divide by the permittivity, is that if we take the divergence of this del V, that should equal to the negative of the total charge divided by the permittivity. So this kind of gives us a relationship of how the charge affects or creates a voltage field, if you want to think of it like that. And it takes into account what medium we're in because the permittivity is in the equation. So this quantity del dot del V, this is a well-known mathematical quantity or concept, and it's more commonly referred to as the Laplacian of V. And so we denote that as del squared V. So that's when you see del squared V, that means del dot V. And so we call it del squared of V. And so utilizing this new definition or notation, then we can rewrite this as del squared V, or del squared of the voltage must equal to the total charge divided by the permittivity in a closed space or volume. So this is known as Poisson's equation. So this is what governs the relationship between the volume charge density in a region and the potential in that region. So you can see here we've got the relationship between the charge and the potential in that region. So this equation then can be expanded as follows to say that it's really just the second derivative of the voltage with respect to x, y, and z is equal to this charge divided by the permittivity. So it's the change and the change of the voltage in each direction. So if we now consider a region in which the charge density is zero, that is, there is no rho zero, then Poisson's equation reduces to this equation. So del squared V is just equal to 0. So this is known as Laplace's equation. It's a special case of Poisson's equation, and it governs the behavior of the potential in a charge-free region. So this equation can also be expanded to say that the second derivative with respect to x, y, and z of the voltage then should equal to 0 if there's no charge present. So let's look at a quick example. These are two equations that are used often in semiconductor physics. So when you're looking at semiconductors as in diodes and transistors, and we're looking at NPN type materials. And so we're going to consider the space charge layer in a PN junction. So this could be a typical diode. We're going to have 0 bias on it. And so that means there's no external field put on this region. And so as shown below, if we define this barrier as x equals 0, for x less than 0, this is a p-type material, so it should be have acceptors, or holes is what we call them, so it's wanting to accept electrons. And then on the right side of the x, or x greater than 0, we'll have a donor type material, or N material. And so it's wanting to donate electrons. It has free electrons that it's wanting to donate. And so there will be some space charge in there because of that. So we want to now consider a space charge density that's given by the material itself, and so we'll have this rho value. And so on the p-type side, it's going to be the charge of an electron, the magnitude of the charge of an electron, times the number, total number of acceptors or number of holes, right? And so that's for this region here from minus dp, which is some arbitrary point we can pick back here, all the way to 0. Same thing on the right side. It's the charge of the electron, the magnitude of the charge of an electron times the number of donors. And again, that goes from 0 to some dn that we're going to pick out here. Again, we need to keep in mind Na and Nd are the acceptor and donor concentrations, so we can concentrate these. We can interject more concentrations. If you get into semiconductor physics, you can study that. But we were more interested in the field effect of what's going on. So when you think of these electronic devices, a diode and a transistor and things like that, we call those electronic devices, but in fact, they are electromagnetic field devices. They are highly governed by electromagnetics. So another reason why I personally feel this course is very important for you to gain some understanding of what's going on. And so again, the dp and dn are the widths of the p and n regions on each of these sides. Okay, so if we look at this charge definition, this will be a graph of that. So from dp, which is that width, all the way up to the barrier, we'll see that we'll have this negative charge density. And then once we get on the other side of the barrier, from the barrier to the width dn, we'll have some positive charge density. So the semiconductor is electrically neutral, so the total acceptor charge must be equal to the total donor charge. So mathematically, we could write this then as this total magnitude times this width, dp, it's got to equal to this total magnitude times this width. And so that's just expressing what we're seeing here, that each side of this vertical axis must be equal. So we now wish to find the potential distribution in the depletion layer and the depletion layer width in terms of the potential difference across the depletion layer and the acceptor and donor ion concentrations. So to do this, we will substitute our charge distribution relationships into Poisson's equation. This is where Poisson's equation comes in handy, right? And so what Poisson's equation tells us then is the second derivative of the voltage. In this case, we only have it in the x direction. Has to equal to these charge distributions divided by the permittivity of those regions, right? And then again, these are for these defined widths here. So we can take the integral with respect to x, and when we do that on the left-hand side, of course, we'll just have the first derivative of x. And then on this side, these are just constants, and so when you take the integral, you'll just add the x component in there, and then we have this constants of integration, C1 and C2. So this is the first step, and it's pretty simple. It's a simple integration. So now moving this forward, we now note that since the electric field is equal to this negative divergence of the voltage, it's simply equal to EX. So the E field lines begin on positive charges and end on negative charges. Hence, they must vanish at dn and dp, which then allows us to write the above relationships as follows. So when we substitute in the width, that's what helps us to determine what these constants of integrations are. So at that barrier, it has to be equal to 0, and so this is what causes that to happen. So if we were to graph that, then we can see at dp and dn, our E field has to be equal to 0, and then at this barrier, they have to equal to each other. And so, we are expecting straight lines because we just have this x variable here, right? So we'll have a straight line down to here and a straight line to bring us back up to 0. So you have to kind of think about this logically to decipher what these integrals of constants of integration are. So you have to kind of have a little bit of understanding of what's happening and what our constraints are. So now with that at hand, we can now solve for the potential difference across the devices by doing another integral with respect to x. So in this case, we integrate with respect to x on the left side, we get our voltage. We do it on the right side, we now get the x squared component of each of these, and we have to introduce another component of integration, or constant of integration. And so again, C3 and C4 are the constants of integration when we do that. So moving forward, we can now solve for these constants of integration by setting C3 equal to 0 and making use of the fact that the potential must be continuous at x equals 0. So again, it's going to have to be equal at that barrier. So if we set C3 equal to 0, that gives us the left-hand side, and so then we can just take the right-hand side as is and put it over here. Again, since x is equal to 0, those terms drop, the second terms drop out. And so when we solve for C4, we come up with this value here, and so it does have contributions from the acceptor and the donor sides. So we can now write the final solution then by substituting the 0 in for C3 and this value for C4. And plug those in. So when we look at a graph of this, this is what our potential difference looks like going across that PN junction, right? So we're starting over here in the P side, we're coming across, and then we get to the barrier. We have this potential, and then we come across here. So that now when we, with the transistor, the way this works then is when we enter a bias in an external field on here, we can move this up and down and make it act like a switch or an amplifier, depending on where you are on the transfer curve. So finally, it's kind of interesting to look at this on a diode. So what we have then is, once we've doped these materials on each side, we'll have these charge densities on here, right? So that's the definition where we started. We have this charge density. So we take that first integral, and when we do, we see we have a representation for the electric field, what's happening inside this region. You can see the E field goes down, comes back up, and then when we take the next integral, the second integral, we show how that relates to the voltage or the potential difference in that region. So this is very illustrative of what goes on inside of a PN junction or a diode. And so we can reverse bias a diode, or we can forward bias it, and one condition no current will flow and the other current will flow. So just another way to look at what's going on in microelectronics.